Welcome to the deep dive. We sift through the sources, find the gems, and basically give you the inside track to knowing what's really going on. So think about your kitchen for a sec. What's that go-to appliance? For so many of us, for years, it's always been the gas range, hasn't it? We all know that whoosh of heat, the blue flame. Maybe you've even used one of those portable ones for a barbecue, or that sizzle.
It's familiar.
Very familiar, almost instinctive.
Right. But there's this new kid on the block, getting really popular, the induction range. Super sleek, talks big game about efficiency, all new cooking vibe. But how does it actually work? What's the science hiding underneath that makes it so different from, say, other electric cooktops that look kind of the same? Today, we're going to dig into that. We're uncovering the invisible fire, powering these things, setting them apart, and all our insights are coming from a great source. Jaejin Chobo, Joryo Majangi by John Byung-chul. And it's really fascinating because it all comes down to this blend, this interplay of electricity and magnetism. These are, powerful forces we usually don't even think about day to day. But with induction, they work together in this really clever way that, well, it just changes how we cook. It's like this unseen energy dance, and we're going to make it visible for you today. Makes a lot of sense once you see it.
Okay, let's unpack it. Starting with the old guard. The gas range. King of the kitchen for ages, and for good reason, right?
Right.
The structure's simple. You see the flame, you control it instantly. Turn the knob, gas flows, spark it up fire. That reliability is why everyone loved it.
Absolutely. Direct control, visual feedback. Very intuitive.
But now, there's a definite shift happening. Induction ranges are stepping up, and honestly, they bring some pretty big advantages to the table. First off, unlike gas, they don't use up oxygen in your kitchen. That's significant.
It's huge for indoor air quality.
Exactly. And no combustion means no gas emissions while you're cooking. So way less indoor air pollution. Just think about the air you breathe at home. Plus, electrically, they're incredibly efficient, like often over 85% efficient. Gas ranges, maybe 40, 55% typically.
Yeah, a huge difference in wasted energy.
Right. So less energy wasted, more heat going straight into the food. That means faster cooking, maybe even lower energy bills. And from a user standpoint, the temperature control is super precise and cleanup. Much easier because the surface itself doesn't get blazing hot like a traditional electric or gas top.
And those points, they really matter beyond just convenience, don't they? If you connect this to sort of bigger trends in home tech, it lines up with this move towards healthier living spaces, safer homes, more environmental awareness, cleaner air, like you said, especially for people with breathing issues. The energy efficiency speaks directly to conservation efforts and that precise temperature control. It's not just for fancy chefs. It means more consistent results, better food safety, less chance of burning dinner.
Yeah, good point.
So it's more than just a new gadget. It feels like a smarter, cleaner way to manage our kitchens and, well, our homes.
Totally see why the shift is gaining traction. Okay, before we get to the real secret sauce of induction, let's clear up something that trips a lot of people up. You see an induction range, and it might look almost identical to, well, a basic hot plate.
Yeah, the flat black surface. I can see the confusion.
Right, both flat, both electric, both heat things up. But, and this is key how they operate is, well, the book says completely different.
Fundamentally different, yes.
So the hot plate, how does that work?
Yeah.
It's actually pretty simple. Think of like an old clothes iron.
Good analogy.
It's got a heating element inside, right? That gets hot. A hot plate is basically the same idea. There's a heater coil under that cast iron or coated plate. That coil heats the plate directly, and then the hot plate heats your pan through direct contact. Simple conduction. Touch equals heat transfer.
Classic heat transfer. Element heats surface, surface heats pot.
Exactly. And that method has its pros and cons. Pro hot plates are usually cheap, and you can use literally any pot or pan on them. Glass, ceramic, aluminum, whatever.
Total compatibility, that's a plus.
But the cons are pretty significant. They use a lot of electricity. They lose a ton of heat just radiating out into the kitchen because the whole plate gets hot. And of course, there's a real burn risk. That surface stays hot for quite a while after you turn it off. Gotta be careful.
And that is the crucial dividing line. Hot plates. Direct heat. Element gets hot, touches the pan, pan gets hot. Simple, sure, but inefficient. Wastes heat, burn hazard. Induction. It just throws that whole direct heating idea out the window. It uses a much smarter, invisible process, electromagnetic induction. And understanding that difference is why induction ranges are, well, in a whole different league. Here's where it gets really interesting.
Exactly. That invisible part is the secret. Electromagnetic induction. Sounds fancy, maybe a bit like magic, but it's pure physics. So let's break down step by step how this invisible heat actually gets generated inside the range.
Uh-huh.
Okay, first, underneath that smooth ceramic top, hidden away, there's a coil of wire, a special internal coil. When you switch on a burner, a high-frequency electrical current, we're talking maybe 25,000 times a second, super fast starts flowing through that coil.
Uh-huh. A rapidly oscillating current.
Right. And this fast pulsing current creates something else, an electromagnetic field. A magnetic field that pulses just as quickly. This field projects straight up, passes right through the ceramic glass, doesn't heat the glass itself, and reaches the pot or pan sitting on top.
And this is where the cool part happens. If, and this is a big if that pot is made of the right stuff, a conductive material like stainless steel or cast iron, that magnetic field from the coil, it actually creates electric currents inside the metal of the pot itself. They're called eddy currents.
Eddy currents,
Yeah.
like little whirlpools of electricity.
Exactly like that. Tiny, swirling currents generated right in the pot space. And when these eddy currents flow through the metal, which has electrical resistance, they generate heat. It's called joule heating. Basically, friction from the electricity moving through the metal. The pot itself starts heating up from the inside out, so the pot becomes the heating element, not the cooktop surface. The heat starts right where you need it.
Ah, okay. And suddenly the whole cookware thing makes perfect sense, doesn't it? It's not arbitrary.
Not at all. It's dictated by the physics.
Because the heat comes from those eddy currents in the pot, you absolutely need a pot made of material that reacts to the magnetic field. Stainless steel, cast iron.
Ferromagnetic materials, basically. Things a magnet would stick to, usually.
Right. Those materials allow the eddy currents to form and generate that joule heat. And that immediately explains why your glass bowl or ceramic pot just won't work.
Correct. They don't interact with the magnetic field that way. No eddy currents, no heat. It's a very direct cause and effect.
It's really elegant when you think about it. It's such a
Yeah.
precise system. And this whole method, this induction heating, that's often shortened to IH, right? Induction heating.
That's the one, IH. You see it on appliances.
Yeah, like IH electric rice cookers. They use the exact same idea.
They do, instead of just a heating plate underneath.
They have coils wrapped around the sides of the inner pot, too, so the whole pot gets heated evenly by induction.
Exactly. Leading to reportedly more evenly cooked, maybe even better tasting rice because of that uniform heating. It's the same core principle.
Great real-world example of IH technology beyond the cooktop.
And what's really quite brilliant about this whole system is that the cooktop surface, the ceramic glass, stays relatively cool. I mean, it might get warm from the heat of the pot sitting on it, but it's not the source of the heat.
Right, which links back to safety and easy cleaning.
And keeps your kitchen cooler. Because almost all the energy goes directly into the pot, very little is wasted heating the air around it. If you step back and look at the bigger picture, it's just a fantastic example of these powerful, invisible forces, electricity and magnetism working together in our everyday tech. It takes this abstract physics concept and turns it into, well, dinner. It makes the unseen very tangible.
So it feels like we've really journeyed through the kitchen today. We started with the familiar gas range, understood its appeal. Then we tackled that look-alike confusion with the hot plate, seeing how its direct heating is fundamentally different and where its limits are.
Yeah, cleared that up.
And finally, yeah, we pulled back the curtain on induction.
Yeah.
Uncover that precise and visible science, the electromagnetic induction, the eddy currents, the joule heating, and just thinking about that complex dance of physics happening silently on the counter while you cook. That's the really cool part, gaining that deeper understanding.
It really is. And it kind of makes you wonder, doesn't it? It raises this question. How many other invisible forces or scientific principles are humming away quietly inside the devices we use every single day? You know, from the phone in your hand to the microwave to how Wi-Fi works. There's so much science happening just beneath the surface. So maybe take a moment, look around, and just consider the deeper mechanics at play. It can make the ordinary feel pretty extraordinary when you stop to think about it.
That's a great thought to end on. Look beyond the surface. Well, thank you for joining us on this deep dive into the invisible fire. Until next time, stay curious.